right? So yeah, so if it is resonance, your imaginary part of the impedance will be completely eliminated. So if I draw the response curve, right, for example, if I have a circuit, right, LCR circuit, along with the function generator, right, this is R, L, C, and if it is current I, right? So we can draw the frequency versus I, right? So in your y-axis, you can take the frequency and, sorry, y-axis will be current and x-axis will be frequency. So you will have a graph something like this, right? Where you have your maximum value at omega naught, right, which is your resonance frequency. So omega naught equals resonance frequency, right? Okay, so this will be your I max. Am I right? This will be your I max, right? So I max will be simply V out over, right? So because at resonance conditions, this will be 0, right? At resonance, we can simply assume that the j omega L given by the inductor and 1 over omega C, 1 over j omega C introduced by the capacitor will cancel each other. So effectively at omega naught, you will have the resistance only, right? You will have your resistance value only, right? So if you take it as V naught, you can put I naught as V naught over R. Am I right? So maximum current will be, because yeah, imaginary part will be 0, which is 1 over j omega C plus j omega L is 0. Right now, yeah, we have a parameter called I max, and you can see that the response is like a curve, right? Like a curve. It is not kind of a sharp, right? It's not something like a spike on omega naught, right? Hence, we use another factor or quality factor to measure the sharpness of this one, right? The how sharp the graph is, right? To calculate the quality factor, what we do is simply we point I max by root 2, right? I max by root 2, right? And then I'll put a line here, right? So this curve will intersect with this line at 2 places, right? This is 1 and this is 2, right? So what I can simply do is I can mark this as omega 1, right? Let this be omega 1 and this as omega 2, right? Omega 1 and the other one as omega 2, right? So here we use a term called quality factor. Right? Or we can simply represent that by Q, right? Quality factor or Q, right? So quality factor is actually will give you an idea of how sharp your resonance curve is, right? So what you can do is your quality factor Q is simply defined by omega naught by the difference between these two frequencies, right? The difference between these two frequencies means, so omega 2 minus omega 1, right? And this omega 2 minus omega 1, or the frequency in between, is called as the bandwidth. Bandwidth. Right? You will use this term in many other places in electronics, right? When you are using analog electronics or analog amplifiers, you will be using, or you will be talking about the term bandwidth a lot of time, right? So bandwidth means within this frequency, right, you will have a current which is greater than I max over root 2, right? So within this frequency, you can say that your output current is significant, right, in this region. Right, now let's see how we can calculate this one, right? Let's see how we can calculate this one, right? So okay, so what is your I max? We can say that at resonance frequencies, I max equals, simply you can write it as V naught over R. Right, so now let us calculate what will be, or at what is the resistance when you are at I max by 2. Right, so okay, at omega you can write to, if it is a series resonance circuit, I can write it as R squared plus omega L, right? Omega L minus 1 over omega C into J equals, right? At this will be at right. So at these two frequencies, right? At omega equals omega 1 and omega 2, I can say that that is, yeah, I max by root 2, which I can say that, right, the resistance is twice, right? So I can simply write it as, right, so if it is root 2 R, right, it will be 1 over root 2 R. So I can write it as, if it is whole square, right, so R squared into whole square will be simply 2 R square, right? Why? Because the current is just simply by root 2, right? So when you put another one, you will have this one. Right, now I can simply write this as, right, I can bring this R the other side, so 2R become R. So I can write it as omega L minus 1 over omega C equals, right, because I am removing the plus, sorry, yeah, J will not be there, right, because I am writing the mod value, right? So I can write it as plus or minus R. Am I right? So when you are moving this one, this becomes R and R square and omega L minus omega C squared. Just take square root both sides. So you can write it as omega L minus 1 over omega C equals plus or minus R. So I can say that if it is plus R, it could be either omega 1 or minus R, it could be omega 2. Clear? Right, I can simply assume it as for those two frequencies. Right, so okay, let omega 1 L minus 1 over omega C equals plus R and, sorry, omega 1 and omega 2 L minus 1 over omega 2 C equals minus R, right? Okay, let this be in, yeah, minus R, right? From these two, what we have to calculate is, we have to calculate omega 2 minus omega 1, because we already know what omega naught is, right? So yeah, so simply what we can do is first add these two together, right? Simply add these two together, right? So plus R minus R becomes 0. So I can write it as L into omega 1 plus omega 2, right? So minus 1 over C into, right? Yeah, you are adding these two together now. So 1 over omega 1 plus 1 over omega 2 equals 0. Am I right? So I'm just simply multiplying, right? Just multiply everything by C, right? So LC into omega 1 plus omega 2 minus 1 over omega 1 omega 2, right? If I take these together, I can write it as omega 1 plus omega 2. Am I right? Equals 0, right? So I can multiply this with this with this, and then I can bring it to the other side, right? I can bring it to the other side. So right, just tell me if you cannot see anything, any portion. So if you cannot see something, right? So Right, so yeah, what I can do is LC into omega 1 plus omega 2 equals, right, omega 1 plus omega 2 over omega 1 omega 2. Am I right? So simply we can remove these two together because these two are positive, right? They are not my zero, not equal to 0. So I can simply write it as omega 1 omega 2 equals 1 over LC. Right? Right. So what is the frequency, resonance frequency you had for resonance in LCR circuits? What we had is, yes, omega squared equals 1 over LC, means 1 over root LC, right? So omega naught equals 1 over LC. Right, so now what I have here is 1 over LC, so I can write it as omega naught squared. Am I right? So omega 1 omega 2 equal to omega naught squared. That means the multiplication of these two frequency is equal to the omega naught squared. Right? Okay, now just subtract these two. This one minus this one, right? So how we can write that one, right? When I'm subtracting this one, right? This is 1 and 2, right? This is 1 plus 2. This is just 1 minus 2, right? So when you are subtracting it, how can you get it? Yes, so L into yeah, omega 1 minus omega 2, right? So and then while you are subtracting it, minus, right? So minus, I would say I can make it as plus, right? Because there is already a minus, so I can put it as, yeah, so I can take it minus, so omega 2 minus omega 1, right? It will be omega 2 minus omega 1. Sorry, yeah, but I can put minus here, right? So this will be, right? So minus 1 over omega c minus, right, this one. So this will become plus omega 1c. This will be 1 over omega 2c, right? Which is equal to 2r, right? R minus minus r become 2r, right? Now we can solve it, right? So if you simplify it, L into omega 1 minus omega 2, right? So now you can make it as plus, right? So this will be simply okay, take it minus, right? So another minus means you can make it plus, so will be, oh sorry, yeah, 1 over omega 1 minus 1 over omega 2, because we took minus common, into 1 over c equal to 2r. Clear. Again, now I can took the LCM. So what I can do is L into omega 1 minus omega 2 plus omega 1 omega 2 over omega 2 minus omega 1, right, into 1 over c equals 2r. Right, this is equal to 2r. Right, so yeah, what I can do here is yeah, so I can took omega 1 minus omega 2 as common, right? Omega 1 minus omega 2 as common, so I can simply write it as yeah, this will be yes, I'm taking it out, yes, so this will be L, right? So omega 1 minus 2 minus yeah, so when it comes, 1 over C into, what is omega 1, omega 2? What we have done here is omega 1, omega 2 is simply 1 over LC, right? So if it is 1 over LC, LC will go on top, right? So this will be plus, so, right? Equals 2R, right? So C becomes omega 1 minus omega 2 will be equal to, right, 2R. So 2R over 2L. Omega 1 minus omega 2 equals to R over L. Right now, substitute these two in this equation. Here, so what is omega naught, which is square root of 1 over LC, right? So if I write it, Q equals omega naught means square root of 1 over LC by omega naught minus omega 2, sorry, will be R by L, right? So simply L will go on top. I can write it as L over R into square root of 1 over LC, right? If this L go inside, right, so that will become L square, right? So L will get cancelled, so I can write it as 1 over R into square root of L by C, right? So this will be your quality factor, right? This will be your quality factor, right? So using this equation, what you can say is, right, if you have a high resistance, right, if your resistance is high, then what will happen to your quality factor? Yeah, if it is high, then your quality factor will be low, right? Quality factor will be low, right? For what I can say is, if your resistance is high, you will have your resonance something like this, right? If you have a low resistance, relatively low resistance, it will be getting sharper, right? It will be getting sharper, right? So that's what your quality factor say about the resonance frequency.